Now we're going to do some examples where we find the value of a log. So it might just say, what's log of 100? And you've got to find that. Well, on this one you could use a calculator because it is log base 10, understood to be log base 10. And when it just says log of 100, you could put in your calculator log of 100. So you can try that now if you'd like. The answer should be 2, but let's see why. So if we didn't have our calculator, what we would do is we would kind of write this more specifically. So we're saying log base 10 of 100 is what? And I'll let the what be x. So remember, if it just says log and there's no base, you understand it to be a 10. That's a log base 10, understood. And then you have log base 10 of 100 is what? So the most logical way for us to figure out what this is to rearrange it into exponential form, because log doesn't mean anything to us this early in the game to really understand what log of 100, why would that be 2? And it's because, remember, log backs. So what that means is that b is the base of your exponent, so we're going to put 10 as our base. X is the exponent, and so we're going to put x as our exponent because it's not given. And then we're going to say equals our answer, and our answer is the 100. And so if we think of it this way, 10 to the what power equals 100, that's something we know off the top of our heads, that 10 to the second power is 100 because 10 times 10 is 100. So we know that x equals 2 in this particular case, just because we know about exponents. And because of that, you can say log of 100 equals 2. The problem with using a calculator for these all the time is that we don't have anything on our calculator but log base 10 and log base e, which is the ln, the natural log. And so we don't have a way to put in a base right now with most calculators. Some of the newer calculators do have a way, but we're going to just talk about this logically for a minute. So log base 8 of 32, just doing what we did last time, log base 8 of 32 is what? Well, it's then saying as an exponent that 8 to the what equals 32. That's the equivalent expression or statement. This statement and this statement really mean the same thing. The problem here is now that we don't know what 8 to the what power is 32 because it doesn't come out nice. I mean, 8 to the first is 8, 8 to the second is 16, 8 to the third is bigger than that. And so we have no idea what x is. But there is a little trick that you can do. If you can find common bases here and here, we will be able to do it. And one of the common bases that we look for first is to see if it could be written as 2 to the some power. And this will make sense when you see what I do with it. If it's not 2 to the some power, try 3 to some power or 4 to some power. It's usually going to be a small number if they give it to you in this form where you have to figure it out yourself. So what we're going to do is rewrite 8 as 2 to the third because that's the same thing. And we're going to rewrite 32 as 2, and you could play around with it on your calculator, but it's 2 to the fifth power is 32. And so I'm just taking the 8, rewriting it as 2 to the third power, taking 32, rewriting it as 2 to the fifth power, and then notice that the 8 has an x power on it already, so we still need that x power there, and we put the equal sign, and 32 didn't have a power on it, so we'll just leave it like it is. Now let's think about what that equals. We have a rule that says if you have a base that's being raised to 2 powers, that you can multiply those powers, so that would be 2 to the 3x, would be a shorter way of writing the same thing, and then equals 2 to the fifth. Now we're getting real close to the answer. The next thing I'm going to show you is up here in the green. This is just a rule of exponents, that if if you have a to the m equaling a to the n, and the a is the same base, then wouldn't it make sense that m and n would have to be equal to one another? In other words, if you said a to the 2 equals a to the something, wouldn't n have to be 2 in this case? Because a to the 2 would have to equal a to the 2. So if the bases are the same and they're saying they're equal, then the exponents are also going to have to be the same. Because of that fact, now that we have the same bases, which is what we want to shoot for when we change these to some kind of base, we want to shoot for the same base, then because the bases are the same, the exponents would have to be equal as well, because this statement says equals. They couldn't be equal if 2 was to the 5th power and the other 2 was to the 2nd power. It wouldn't be equal. So that if the bases are the same and they're saying it's equal, then the two exponents have to be equal. And so because of that, we can say that it has to be true that 3x equals 5. Those exponents have to equal one another if this equation is truly going to be equals like it says. And then because of that, we can now just solve this for x. And so I'm going to divide this by 3, and get x equals 5/3. Can't be reduced, so we'll just leave it 5/3. So the number we were looking for in log base 8 of 32 is actually 5/3. And as an exponent, I could have never told you that 8 to the 5/3 was what gave you 32. But it does, and that's the right answer. And this is the best way to go about finding it, is find a common base between the two numbers, like 2 in this case. And if you can find the common base, you can eventually get to where you can use this rule up here in green. The last example I want to show you is what you do when something looks like this. So it's a log base 64 of 1/32. I can guarantee you when you're messing with a 64 and a 1/32 that there's going to be a negative exponent involved somewhere in this problem, because something is going to have to flip it over or put it on the bottom. So let's see what happens. So I like to set my log that I'm trying to find and say log base 64 of 1/32 is what, and let the what be x, just so that I can then see how to rewrite it, that it's 64 to the x. That would give me a 1/32. And that's just rearranging from log form to exponential form. Then, like we said in the last problem, you want to get a similar base. And we're going to try 2. 2 is the most common one. It doesn't have to be 2. But can you go to your calculator and figure out 2 to the something that will equal 64? And then go to your calculator, or just think about it logically, 2 to the what would equal 1/32. So let's look at each one. 2 to the 6th power is what we would write there, because 2 to the 6th power is just replacing the 64. And then we still have the x power on the outside. Then we have 2 to the something that would equal 1/32. Well, 2 to the 5th is equal to 32. So if you want that 32 to move to the bottom of the fraction, you're going to have to say 2 to the negative 5th, because a negative power will push that 32 down to the bottom. And so that's what we're shooting for. 1/32 is actually 2 to the negative 5th. Then there's an exponent rule that says if we have a base to 2 powers, we are allowed to multiply those 2 powers. So we'll just put them side by side as multiplication. And this other one is just a 2 to the negative 5th. If our bases are the same, and it's saying that these two things are equal, the only way they could be equals is if their exponents were the same. So we're going to set the exponents and say this has to be true, that 6x equals -5. And because of that, we can now solve by doing whatever it takes to get it by itself. So x equals -5/6. So the answer to this question is -5/6 when you do log base 64 of 1/32. The answer is -5/6. And again, that would not be something you could figure out easily just by looking at it. And so you're going to have to do this similar base, this same base rule of making them into the same base so that we can say that the two exponents must also be equal.